Hello everyone, I am Pallavi Ingre. Today's topic is Z transform. The points we'll be covering in this lecture are introduction, relationship between Z transform and DTFT, convergence, region of convergence of Z transform, and properties of ROC with examples. Until now we have seen the transforms like CTFT, DTFT. Especially DTFT is applied on discrete time signals to study the discrete time signals and the properties of LTI systems, linear time invariant systems. Now Z transform is another transform which is also applied on discrete time signals. So there is a question that why there is another transform which is applied on discrete time signal when there exists a transform like discrete time Fourier transform. In short, we call it DTFT. So why Z transform is required? So the importance of Z transform is that Z transform exists for many signals that do not have DTFT. So we'll see the definition of DTFT first. We call Fourier transform x of e raised to j omega is equal to summation signal x of n. This signal is discrete time signal multiplied by e raised to minus j omega n. N varies from minus infinity to infinity. But the important condition for the convergence of DTFT that the signal must be absolutely summable. This sum should be less than infinity. That the signal x of n must be absolutely summable. So what is the difference between Z transform and DTFT? We will see the definition of Z transform. In short, we call it ZT. So x of z is equal to x of n multiplied by z raised to minus n. So here there is a different complex variable z. So z is r e raised to j omega. So what is this r e raised to j omega? This is a polar coordinate representation. So we'll draw the circle of radius r, angle omega. So this point is z is equal to r e raised to j omega. So r is mod of z and angle of z is omega. So this is real part of z, this is imaginary part of z, and this whole thing is z plane. So this is magnitude, this is the angle of z. Now when we put z is equal to r e raised to j omega in this definition, see what happens. X of n, instead of z we'll put r e raised to j omega. R e raised to j omega raised to minus n. R raised to minus n, e raised to minus j omega n. So this thing, if you consider this thing as a signal, this is same as definition of DTFT. So this thing should be absolutely summable. So this modifies the signal. The multiplication by an exponential convergent factor r raised to minus n makes this signal x of n absolutely summable, and we can take the transform of this signal. The signal becomes absolutely summable. but this depends on the values of R. What are the specifically values of R for which the signal becomes absolutely summable? So suppose we take the example of U of n, x of n is equal to U of n. You know that this signal is series of ones starting from 0 to infinity. If you multiply this signal with an exponentially decaying signal like this, so this multiplication of x of n with r raised to minus n. So this is an exponential decaying signal. When it is multiplied with this u of n, the signal becomes like this, and this becomes absolutely summable. This is like taming a wild signal. So you want this signal to be absolutely summable. So that's why you are doing modifications by multiplying this signal with exponential convergence factor. Now you can think about the relationship between the Z transform and DTFT. Now this is DTFT of the signal x of n multiplied by r raised to minus n. So when the value of r is equal to 1, we change here, r is equal to 1, this definition x of z, this becomes, the value becomes 1, 0. So when r is equal to 1, the definition of x of z is similar to x of e raised to j omega. Means Z transform of signal x of n is equivalent to Fourier transform of the same signal when mod of z is equal to r. This value we will consider as 1. So this is the relationship between Z transform and DTFT. So again we can draw a simple conclusion from this thing, that Z transform calculated on this unit circle when this value of r is equal to 1, this represents the DTFT of the same signal. Now we will turn towards the region of convergence. So what is region of convergence? Region of convergence of Z transform is the values of r for which the Z transform converges. Means this value of Z transform x of z does not goes to infinity. That is called as region of convergence, and in short we call it ROC. So see the region of convergence, properties of this region of convergence. We will see some examples. These are very classic examples of Z transform. So first we will consider x of n, a signal a raised to n u of n. So to take the Z transform of this signal, we first write the definition. Put the value of this x of n. Now because this u of n signal start from 0 to infinity, we will modify the unit limits of n from 0 to infinity, a raised to n, z raised to minus n. So we can write this as a z inverse raised to n. Series summation formula is applied, 1 divided by 1 minus a z inverse, where this value should be less than 1. Less than 1. So this mod of a should be less than mod of z. So we can call mod of z should be greater than mod of a. So this is a condition which is required. So we represent this condition in Z plane. That is nothing but the region of convergence we are drawing. We'll draw a circle of radius A. A pole is here. See this denominator. 1 minus AZ inverse is equal to 0. So Z minus A is equal to 0. Z is equal to A. So at Z is equal to A, there is a pole. So mod of Z must be greater than this mod of A. So this region is outside the circle of radius A. So this is your region of convergence for this x of n. Now see another example. So in the first example, we have seen a causal signal, and this is typically an anti-causal signal where u of minus n minus 1, and draw like this, u of minus n minus 1, the signal starts from minus infinity to minus 1. All the values are ones because it is a unit step signal is flipped. So to find the transform, we will put this into the definition signal. Minus a raised to n u of minus n minus 1 z raised to minus n. Now we'll take this minus sign outside and put this limits. N is starting from minus infinity to minus 1, a raised to n, z raised to minus n. Now flip this sign of n. Minus n starting from 1 to infinity. Minus infinity change to infinity, minus 1 change to 1. And this n will be changed to minus n. So a raised to minus n, z raised to n. A inverse z raised to n. Now we are going to apply the formula. Similarly we have applied here, but this limits are starting from 1 to infinity. We want it from 0 to infinity. So we will take a variable, different variable. Instead of n, we will take a different variable m. So n minus 1 is equal to 0. We want it 0. So we will put n minus 1 is equal to m. So this m, now n is changed to n plus 1. So when the value of n is equal to 1, the lower limit, at that time, in this formula we put that value n minus 1 is equal to m. So m will become 1 minus 1, 0. So n is equal to, when it is infinity, n will go to infinity. So we put a new variable, this m is equal to 0 to infinity, a inverse z raised to, now n is replaced by n plus 1. A inverse z raised to n multiplied by a inverse z. We take out this a inverse z and apply the formula here. 1 divided by 1 minus a inverse z. Now we multiply this by az inverse, and when we are applying this formula, this value a inverse z should be less than 1. So mod of z should be less than mod of A, and we'll do this multiplication. After that we'll draw the ROC. Now this will become minus 1, AZ inverse minus 1. So that minus sign 1 minus AZ inverse. We'll draw this ROC. A circle of radius A again. Z minus A is equal to 0. So Z is equal to A. That is a pole at Z is equal to A. And this condition is mod of Z is less than mod of A. So this area is like this in the Z plane. So the ROC for this example will look like this inside the circle of radius A. Now there is a very important thing to observe comparing these two examples. This is a causal signal, this is an anti-causal signal. For these two different signals, we have same value of x of z. X of z is same, 1 divided by 1 minus AZ inverse. But the ROC is different. Mod of z greater than mod of A. Here mod of z less than mod. So this is the difference. We need to point out here that the ROCs are different for these two examples, but the value of x of z is same for these two. So the mentioning ROC while solving x of z is very important. Now we'll see combination of examples. Third example, we take some values. X of n is equal to half raised to n u of n plus 2 raised to n u of minus n minus 1. Now as we have solved the examples, we'll directly write the answer for x of z, as we have just changed the value of that constant here. So this will become 1 divided by 1 minus half z inverse. Now this sign will change, as there was sign in the x of n itself. So x of z was positive. So here sign will change. 1 minus 2z inverse. Okay. So for this part, specifically this part, the ROC is mod of z greater than mod of half, and for this mod of z less than this constant 2. Combining this 2, greater than half and less than 2, so we can write this as, this is the combined condition for ROC of this example. So we can draw this combined condition by drawing two circles like this. So we have two poles in this example. One is at half and one is at 2. So the combined region is in between these two circles. Now similarly, we'll take another example. X of n is equal to half raised to n u of n plus 1 by 3 raised to n u of n. So complete signal is causal. Here it was combination of causal and anti-causal signal. Here it is combination of two causal signals. So we can write the answer of x of z, 1 divided by 1 minus half z inverse plus 1 divided by 1 minus 1 by 3 z inverse. For this part, mod of z greater than half, this part mod of z greater than 1 by 3. So in combination we can write the ROC for this example. So the combined area mod of z is greater than half. So I can draw this way. Circle of radius half. Here it is a pole at 1/3. Here it is a pole at 1/2. So the combined area is outside the circle of radius half. So ROC must not contain a pole inside this ROC. Pole is not contained. So when X of n is combination of two causal signals, it is having two poles. So we are taking the area which is combined and which is not covering both of these poles. So outside the outermost pole is the area which we call region of convergence for this example. Now we'll look at some different examples. Finite duration signals. Now we have seen infinite duration signals. So we'll take example number 5. X of n is a signal like this. 1, 2, 3. So x of z is equal to now we'll write first the definition. X of n z raised to minus n. So this is this definition like this: x of 0 z raised to 0 plus x of 1 z raised to minus 1, and so on this side, and so on x of minus 1 z raised to 1, and so on this side. So we can write like this: x of 0 is 1 z raised to 0, so that is 1. X of 1 is 2 z raised to minus 1, 2z inverse, and that will be plus 3z raised to minus 2. So this is 1 plus 2 by z plus 3 by z square. So we can't put the value of z is equal to 0, as this answer will go to infinity and the x of z will not converge. Therefore we can't put the value of z is equal to 0. So we can draw ROC like this. It is complete z plane except the value z is equal to 0. So ROC is entire z plane except z is equal to 0. So this is a causal signal, finite duration signal, for which the ROC is entire z plane except z is equal to 0. I'll see the next example. We'll take a simple signal, anti-causal signal like this. 0 is here. So this is an anti-causal signal. You can write x of z as 3z square plus 2z plus 1. So we can't put the value of z is equal to infinity, because this will cause x of z to be infinity. So for this example, you can draw the ROC. Again, the entire z plane ROC is entire z plane except z is equal to infinity. Now I will take another example, combination of this two. Like this, 0 is pointing here at 1, and write x of z as 3z square plus 2z plus 1 plus 2z inverse plus 3z raised to minus 2. So we can't put here z is equal to 0 in this case, and z is equal to infinity in this case. So both conditions are applied in this ROC. Entire ROC is entire z plane except z is equal to 0 and z is equal to infinity. Both values are not allowed and the entire Z plane is included. So we can summarize the properties of Z transform we can summarize the properties of ROC. So each and every case we have seen that the ROC is a ring type, circular type region in the Z plane and it is centered about origin. Okay. So this is the first condition. ROC of x of z consists of a ring in Z plane centered about origin, and x of z is rational. Rational means numerator and denominator kind of answer we got in Z, x of z. At that time, ROC must not contain any poles. So we have seen in the example this. ROC must not contain any poles. If you go and solve an example for combination of two anti-causal sequence, so the region will be inside the two poles. So it will not also cover the poles. This will cover the region inside the innermost pole. Okay. So it must not contain any poles. Now finite duration signals, as we have seen in the example. Finite duration signal, if the signal is causal, so the ROC is entire Z plane except Z is equal to 0. If the signal is anti-causal, like this, ROC is entire Z plane except Z is equal to infinity. If the ROC signal is two-sided, containing both right hand side and left hand side of the signal, then the ROC is entire Z plane except Z is equal to 0 and Z is equal to infinity. Both the conditions apply. Now, infinite duration signals. If the signal is causal, like this, right-handed signal, infinite duration, then the ROC is circular. It is a region outside mod of Z greater than this R. If the signal is anti-causal, the ROC is inside the innermost pole of radius R. If the ROC signal is two-sided, then ROC consists of a ring between these two poles, R1 and R2. So we have seen with the help of examples, we have proved the properties. Thank you.